The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone. Thank you for joining us today for our webinar discussing HRX Wells demonstration of a new technology for passive in situ remediation with our speakers Dr. Craig Devine, technical expert and vice president with Arcadis, and Dr. Michelle Crimmy, director of engineering and management and professor with Clarkson University. I am your moderator today. My name is Dylan Kemmer, and I am our lead generation specialist with Caris Corporation. Come on. Here we go. A few housekeeping items before we get started. All attendees are in listen-only mode to help cut down on any background noise. If you have any questions, we encourage you to submit those throughout our presentation using the question pane in the GoToWebinar panel or email us directly. If you submit questions through the GoToWebinar, we will receive a report with the question and your contact information to follow up directly after the webinar. If you are interested in receiving a PDF or recording of the presentation, please contact us. We encourage you to share the recording with your network. Here are a few ways to find us. We have listed our website and general sales and marketing email address. Do you receive our email blasts for upcoming webinars, presentations, trade shows, and technical information on our various solutions? If not, sign up on our website. You can find the Join Our Email list on any landing pages on the right-hand side. Be sure to select the industry when signing up to ensure you receive the most targeted information for your needs. And we can't forget to mention our social media platforms. We encourage you to connect with our Caris Corporation page, as well as our team members on LinkedIn, where we are often sharing upcoming events, including webinars, industry articles, or news, sharing relevant posts from other industry experts, and more. Follow up on our YouTube, Twitter, and Facebook pages as well. If you are interested in any of the upcoming webinars, here we list our webinar landing page where you can find the upcoming webinars, registration info, as well as our on-demand webinars recorded previously and available for you to view at your convenience. Here we have listed our contact information for Caris. We have our U.S. sales reps, Troy and Tim, for Canada, Mexico, and South America. We have Louis, and our European sales, you can contact Lorenzo. For our lab, we have Cody Zaitone, who manages all of our remediation analysis. If you are interested in any of our marketing materials, including the recording of this presentation or a copy of the slides, you can contact myself at the email listed. For general inquiries, you can either email our contact email or call our switchboard. Also, you can visit our website at www.cariscorporation.com. At this time, I would like to take this opportunity to introduce our speakers. First, we have Dr. Craig Devine. He is a technical expert and vice president at Arcadis US Incorporated with more than 20 years of experience in subsurface characterization and remediation. He has extensive experience remediating large chlorinated solvent plumes, utilizing a wide range of technologies, including bioremediation, in situ chemical oxidation, permeable reactive barriers, co-solvent surfactant flushing, and directed groundwater recirculation. He is the co-inventor of the horizontal reactive treatment well, HRX well, and the mini trap. Both technologies are currently being demonstrated and validated through ESTCP projects. Dr. Devine is a leader in Arcadis' site evaluation and remediation technical knowledge community and is responsible for ensuring that Arcadis' technical expertise is best applied for our clients' benefit and to ensure that project goals are achieved. Next, we will have Dr. Michelle Crimmy. Dr. Michelle Crimmy is the Director of Engineering and Management and a professor jointly appointed in the Ray School of Business and the Institute for Sustainable Environment at Clarkson University. Her areas of research interest include the development of in situ remediation technologies for treating contaminated groundwater, chemical oxidation of organic contaminants, impacts of in situ remediation on aquifer quality, and the integration of treatment technologies for optimized risk reduction. She has been PI or co-PI on several research projects focused on the treatment of groundwater contaminants, funded primarily by the Department of Defense Strategic Environmental Research and Developmental Program, SCRDP, and the Environmental Security Technology Certification Program, ESTCP. Her projects are often conducted in partnership with industry and consulting organizations and often have a strong technology transfer focus with the objectives of moving technologies from the laboratory to full-scale adoption by developing guidance, tools, protocols, and workshops to support field application. And that's all. Go ahead, Craig.
Okay, great. Well, hey, thanks, Dylan. Thanks, Karis, for this opportunity. Thank you to all of you on the line for spending a little time this afternoon. Michelle and I are really excited to share with you the horizontal reactive media treatment well concept. I think it's got some interesting, unique features and some potential broad applicability to a wide range of environmental challenges. And we've got some data from an ongoing performance demonstration project that I think you'll find pretty interesting. So what is an HRX well? It is a large diameter horizontal well. And when I mean large diameter, I'm talking 6, 8, 12 inches in diameter, or even larger if possible. That's installed along the groundwater flow path, and it's filled with a reactive media. So if we have a conceptual aquifer here, the triangle represents the water table, the brown is the unsaturated zone, and flow is left to right. You could install this large diameter well, in this case it's a double-ended well, below the water table, again along groundwater flow direction, and then exiting on the down gradient side. And in this case, there would be a screen on the left side, on the up gradient side, and a screen on the down gradient side, and then a cased section in the middle. And because this large diameter well has a much higher permeability than the surrounding formation, it acts as an engineered high permeability feature, like a fracture or a karst conduit. And therefore, there will be a flow focusing phenomena. That is, groundwater will preferentially flow into that well. And then, of course, while it's in that well, if it's contaminated, it will react with some type of reactive media present in the well, and then flow out the down gradient side treated. And so, in a sense, you could consider it a passive reactive barrier form of a PRB. And so it has many of the advantages and similarities of a more conventional PRB, like a trench-based PRB. It's a flux control technology, and it's passive. There are some, I think, distinct advantages, though, to this sort of configuration. First is that, of course, you're not as depth limited. Horizontal wells can be installed at much greater depths than trenches, and certainly from a cost perspective, that difference becomes greater as you go to deeper depths. It has a limited above ground footprint. There's no ongoing operation or maintenance requirements. I think one of the more distinct aspects to this compared to a conventional trench-based PRB is that because groundwater is then focused into that horizontal well, the media usage is very efficient. In many trench-based PRBs, you may have zones of the PRB that don't see a lot of contaminant flux, and yet you need to put media there. And so at the end of the day, you end up using quite a bit of media. And in this case, because of the efficiency of the hydraulics, much less reactive media is used. And I think that creates an opportunity to use much more expensive media because you're using much less of it. So the opportunity to have more tailored or designer media is represented. And there's also the potential to use multiple media types in series to address either pretreatment needs or multiple contaminants. I present this concept at a few forums, and sometimes the hydraulics are a little bit complicated to envision if it's the first time you've seen it. So I put together this really simple numerical flow and transport model using pFlow, which is a USGS Java-based code, really simple to use. And this is a plan view of an HRX well. So the white represents the surrounding aquifer. The blue would represent the well itself, so a very high permeability. And then the green is the cased section, so no flow across that green. So the blue is a very high permeability zone. The green is a very low permeability zone, and the white is sort of a middle permeability zone representing the ambient formation. And of course, this is simply two-dimensional, but it helps understand the hydraulics. So I ran this video, or ran the model, put it into a video, and I'll sort of talk through as it plays here. Again, flow is left to right. And this is the permeability distribution. So you can see the blue is 1 and the green is 10 to the minus 12, and the white is 0.01. So the first thing that we'll do here is just contour the heads. So you can see the head contours, and you can see them bend around the inlet and out of the outlet, and that's what creates that flow focusing. And we can run flow lines. If we start the flow line right in the center, of course, it runs right through the well, left to right. And if we're at the edge of the domain, it doesn't go through the well, but you can see some bending effect. And as you get closer and closer to the well, that bending effect becomes more severe until those flow lines are captured. And so those flow lines that enter the well, of course, represent the boundaries of the treatment or capture zone. So any flow line that enters the well, and assuming that the reactive media is appropriate, then gets treated. And then on the right-hand side, of course, it's symmetrical. That right-hand side represents the treatment zone. And it's symmetrical top to bottom as well. So you get a similar sort of behavior. And of course, this is a simplified system, anisotropic and homogeneous, but it at least helps you understand this flow focusing effect. And of course, the degree of that flow focusing relates to the contrast in permeabilities and some other kind of specific aspects of the geometry. In this next part of the simulation, I dropped some particles on the left, and you can see how they'll flow. They'll follow those flow lines, but you also see the relative rate of transport. And so the particles in the middle, you'll see, will transport very rapidly. And then you can see the particles at the end that don't go into the well, that bend toward the well, but then eventually kind of pass by, and again are sort of defined by that treatment zone or capture zone. Right, so all those ones that went in the well, and on the right side, that's all treated water. And then these particles that are passing by now, passing by the well, that's the untreated flow lines. And then you can see they sort of bend out and follow the contours of that treatment zone. Okay, hopefully that was helpful. So that's sort of the concept. So how big is that treatment width? You can take a simple approach just using Darcy's law for a simple aquifer and calculate that treatment width. And this equation really is really a relationship between, in the numerator, the amount of flow through the well, so the permeability, the KHRX, the permeability of the material in the well. There, A would be the cross-sectional diameter, and I would be the hydraulic gradient across the well. So that's just Darcy's law through the well on the top. And on the bottom, a relationship between the aquifer permeability, aquifer thickness, and hydraulic gradient. And to make it simple, those gradients are similar, although they're a little bit different in a real-world application, but they're pretty similar, so you can sort of strike them out and create a graphic like this that relates the aquifer hydraulic conductivity to the treatment zone width on the y-axis. And of course, these are log scale. And you can see the rough grain size distribution there on the x-axis. And those different lines, the dashed lines, solid and dashed lines, represent different well constructions and aquifer geometries. So for example, that bottom one that says 8-inch diameter well, an aquifer thickness of 35 feet. If the ambient hydraulic conductivity was about 1 foot per day, you can see the treatment width would be about 10 feet, if you follow that up. And in contrast, if you use that middle dashed line, that 12-inch diameter well, so larger well in a slightly thinner aquifer, 20-foot saturated thickness. And if you are in an aquifer setting of about 1 foot per day, what is that? That's about 20, 30, 40 feet treatment width. And this assumes that the media within the well is a hydraulic conductivity of about 1,000 feet. So I think the takeaway, though, from this is that for reasonable aquifer conditions, treatment widths of tens of feet or more are possible. And I think an interesting insight as well is that the treatment width improves with decreasing aquifer permeability. So most in situ remedial technologies tend to perform better the higher permeability conditions you go, particularly if you're an injection-based technology. This is one that actually is, at least under passive operation, tends to perform better at lower permeability settings. And again, that's because that permeability contrast is maximized, which creates a higher or a larger treatment width. But I will note there is a configuration where you could install a downhole pump using a packer system to pump in the inlet side and push through the cased section, and that would allow you to increase your treatment width, particularly in higher permeability settings. But for this presentation, we'll focus on the passive application. So here's some just simplified numerical modeling, more of a 3D application beyond that simple Darcy's Law calculation. In this particular scenario, the well is 300 feet long. It's a 20-foot thick aquifer. The well is 1 foot in diameter. The aquifer permeability is about 3 feet per day, and the HRX material has a permeability, hydraulic conductivity, about 3,000 feet per day. And the average treatment width in this model is about 40 feet, and if you use the equation I showed you before, it calculates to 39 feet, so pretty close. Again, flows left to right. The white lines represent equal head, and in this still you can see them bending on the uphill side, and then you can see them bending on the downhill side, which creates flow in and out. And then the color flood represents the treatment zone. So red would be a starting concentration of 100, and the real cool colors represent clean. And in this particular scenario, actually the whole well was cased. So at any point, particles could flow in and out of the well. And they, for the most part, stay in the well during the run because it's more permeable in the well, and the water does not leave the well until it basically hits the end of the run. And so this model will spin around. You'll see both a plan view and side view. And then sort of near the end, there's an iso shell, green iso shell of the treated zone. Gives you a little sense for the geometry. And I will note there is a kind of a geometry that's interesting, but is somewhat exaggerated because of the vertical exaggeration here. And this is that iso shell I mentioned. So of course you can see that no groundwater up gradient or around the well is directly treated, but immediately down gradient of the well, there is near immediate treatment and kind of a control plane. So again, this is a flux control technology, but does not directly treat source mass or material in high or low permeability materials. Water must come to the well to be treated. I mentioned, I think one of the real exciting aspects to this technology is the potential to use a variety of reactive media types because the reactive media usage is so low. In fact, for the field application that we'll show here in a few minutes, we used zero valent iron to treat chlorinated solvents and only used 1.5 cubic meters of ZVI for the whole thing. And we have a life cycle of decades based on that media. So very little reactive media. So when you start thinking about that, the potential applicability to a really broad contaminant suite is, I think, quite exciting. So these are just some concepts, and Michelle will be talking later about the design model that we're putting together, and some of the parameters from these various media types would be used in that design model to understand the amount of and type of media needed for any specific field application. Okay, so based on this preliminary work, ESTCP funded a field scale demonstration really to validate the technical performance and to understand actual implementability and cost performance data and also sustainability information. And then as part of the final deliverable part of the project, we'll be developing a user tool and guidance. So one of the first things we looked at as part of this was identifying the appropriate reactive media. We had selected a site, in fact, we had targeted using ZVI to treat chlorinated solvents, primarily because that's a well-established treatment technology, and there are plenty of ZVI vendors. So we worked with Rick Devlin at the University of Kansas to test a variety of media types, and we were looking at balancing both reactivity of that media against and alongside with permeability, trying to both maximize permeability and reactivity. Without going into the details, based on that testing, we selected the Connolly iron. And then Rick has also, for a number of years, been working on a technology he calls the point velocity probe, and it's basically an instrument that can go into porous media that facilitates a local scale tracer test. And you can actually see that in the upper right there. That's the instrument itself, and there's a little circle port. And in this case, flow would be from the bottom to the top. And so out of that circle port, a small volume of tracer, a saline tracer or distilled water tracer is ejected. And then you can see two wires, and basically the resistance between those two wires is measured, and that creates that tracer breakthrough curve you see on the bottom there. And because the geometry is well known, that data can be fitted to estimate local scale velocity. So we were redesigning these to place inside the HRX well so that we could actually validate how much flow enhancement the HRX well was creating, and then use that to also calculate the effective treatment with in the field. A couple of key takeaways. We found no progressive loss in permeability or reactivity of the Connolly iron using site groundwater with well over 1,000 pore volumes flushed. And as I mentioned, we selected the Connolly iron, and we were able to modify Rick's PVP design to be applicable for the HRX well setting. And Michelle, maybe I'll turn it over to you on the next couple of slides, let you talk about the work you guys did at Clarkson.
All right, thanks so much, Craig. Just a little heads up, my internet connection is uncharacteristically going in and out, so if you lose me, I'll have to ask you to jump in and take over, but it looks okay right now. At Clarkson University, we conducted lab and pilot tests to validate HRX well capture, hydraulics, and treatment. Our first set of tests were with a relatively small scale laboratory system, which you see as that 55-gallon drum. We essentially created an aquifer in that drum and then placed an HRX well, a mini one, within that tank. We operated it in upflow mode. So it's basically an aquifer tipped over 90 degrees. So the water is introduced at the bottom and flows through to the top. We measured the flow rate through the well and through the aquifer, and we put in a series of piezometers throughout that tank so that we can measure the hydraulic head, and this enabled us to determine the well capture within that tank. We compared this capture to the simulations. You see example simulations there on the left of the tank. So some example results that we got are shown in the top right figure, and what you see there is that as we vary the ratio of hydraulic conductivity in the well to the hydraulic conductivity in the aquifer, as you see on the x-axis, the ratio of flow through the well and through the aquifer responds linearly and as predicted, as Craig talked about earlier. So in other words, the greater the difference in hydraulic conductivity, the more water the well captures. We also conducted tracer tests within this tank. We packed the well with carbon. We used a conservative salt tracer and a sorptive dye tracer, the methylene blue you see in the bottom right figure. And what we found here is that everything behaves as we would want it to. We saw chloride breakthrough the conservative tracer 2 times faster than the methylene blue. The peak concentration was 35 times greater, and the mass that recovered was 20 times greater for the salt at well outlet. So the well was capturing and sorbing that methylene blue dye tracer, like I said, as we expected to. So results looked really good at the laboratory scale. We were able to validate the well hydraulics. We validated treatment with using GAC. And we also used ZVI. We didn't test treatment with ZVI, but we did test hydraulic performance in the lab tank with the well packed with the ZVI. And it's sustained capture and flow through for well over 100 pore volumes of throughput through that tank. So based on the results of the lab tests, we then moved to pilot scale testing. And I have to admit, this was probably the most fun project that we've ever worked on here at Clarkson. They let us build a test pit right here on campus. It's 16 feet long, 6 feet wide, and 6 feet deep. We first modeled the system, as you see on the top left, to simulate flow. We used those simulations under a bunch of different design test conditions to come up with the final design of the well, which you see in the top middle, and as well as to design the monitoring network. We had over 40 piezometers installed throughout the test pit, along with an 8-inch horizontal well. So we measured water levels to prepare contour plots. This allowed us to compare the capture that we actually achieved in the field with those that were simulated, and to make comparisons between predicted and measured values. So example contour plots that we created, you see on the bottom left there. And then based on those contour plots, we could assess the capture width at different distances along the transect, as you see the examples in the bottom middle and bottom right. What we see is the results, again, compared quite well with predicted. It also just simply validated the concept of HRX well passive capture. Our 8-inch well captured a width of over 40 inches of water, and it captured 39% of the flow that was introduced to the test pit, while only occupying 0.5% of the total volume in the pit. So we were able to verify the hydraulic and reactive transport model, and we'll be moving forward with those to create a design tool, which I'll be talking about in a couple of minutes. So with that, back to you, Craig. Thanks.
Great, thanks, Michelle. So based on all that laboratory work and validation of the concept and the numerical model for use as a design tool, we proceeded with field demonstration at the Vandenberg Air Force Base in Central California. This was selected because the aquifer thickness was relatively thin. There was a high concentration of chlorinated solvent, specifically TCE. That was the goal was to control flux from that high concentration zone. You can see that on the plan view there on the right. That purple you can see is over 50 parts per million. In this case, flow is left to right, and the idea was to create a treatment zone in that down gradient screen zone there on the right. Depth of groundwater was about 22 feet. Average hydraulic conductivity was about a tenth to maybe a half a foot per day. So relatively modest to low, and kind of in that zone that you really couldn't inject readily into without high pressures or fracturing the formation. HPT data on the right identified that target zone. You can see the deflections in flow and pressure. Again, represents about 8 to 10 feet, 7 to 10 feet of aquifer thickness. The bottom photograph on the left shows roughly the orientation of the well. In fact, if you see that tree on the left, and then you look in the aerial near the purple there, you can sort of see the outline of that tree, and the well goes underneath this very active road. So this site also, I think, highlights, one of the benefits that it can be readily applied in an area of active infrastructure, very low surface footprint at the end of the day. So in that photograph, that the well basically runs just to the right of that tree, or this side of the tree, almost underneath where the people are standing underneath the road toward that power pole to the right. This is the specific design of the well. There's a cased inlet section on the left there, and then you can see a screen zone. This is a 12-inch diameter well. And then you can see in the middle an empty casing run, and then on the right, screen zone, and then a casing taking it back to the surface. And then you see in the middle several blue squares. Those were the media treatment cartridges. So those are each 10 foot long, and they're bolted together, and they have 35% ZVI, 65% sand. So 4 on the uphill side, 3 on the downhill side, for a total of 70 feet of ZVI. It says 60 on the slide, but it's actually 70. And we didn't need more than that because of the treatment capacity. Again, the total ZVI usage was about 1.5 cubic meters, so very little ZVI needed because of its real efficient usage. And then you can also see some half squares, rectangles, small rectangles on either side of those treatment cartridges. Those are our monitoring cartridges where we place that point velocity probe, the PV probe I mentioned before. So based on the design model, it suggested we would have a treatment width of 40 to 50 feet, or maybe a little bit more, with a residence time of 6 to 20 days in the ZVI. And roughly our model predicts about 100 days of residence time from end to end, screen to screen. As I mentioned, we put PVPs on the inlet and outlet to monitor flow. And of course, we have sample ports in the well itself, in the screen zones on each side, and then nearby monitoring wells. I want to spend a little bit, or just at least share a slide with a little bit more detail on these cartridges. I want to have a shout out to our partners, Directed Technologies Drilling, who really came up with some great practical engineering. These are, you can see on the photograph on the bottom right there, that's one of the treatment cartridges. And they were constructed and filled with ZVI in their shops in Texas, and then shipped out fully loaded to the site. And then those are slid down into the completed well. And we used basically a bentonite collars to create seals between those treatment cartridges and the well, so there's no potential for bypass flow. And then each of those 10-foot cartridges were bolted together, and then on either end, you can see in the left photograph there, essentially the screen inlet that allows water to flow into that treatment cartridge. And you can see the schematics in the upper right is the ZVI or treatments cartridge, and on the left is the PVP or monitoring cartridge. You can see kind of in the center of that cartridge is where that point velocity probe is placed. And in this particular cartridge is just a coarse sand because we're just simply monitoring velocity through that sand. So these are some of the outputs of the final design model. Flow left to right, and again, we went back and forth several times to optimize the design based on what we were seeing on the numerical model. And I would just say that's a kind of a takeaway. That first equation I shared is a good starting point to understand likely performance, but site-specific numerical modeling is probably going to be required in most field applications because they're aquifer geometry aspects and sensitivity testing that can really only be considered when using a numerical flow and transfer model. So our final model suggested that at a kind of optimal performance would be maybe a little bit higher than 50 feet, 50 to 60 feet. You can actually see the treatment width on the right side is smaller than the treatment width on the left side, and that's because in that part of the aquifer domain, the permeability is higher. So there's still the same amount of flow, but the permeability is higher, and so the actual hydraulic zone of influence is a little less. And actually I have a video of some of the numerical design model output. You can see the orientation, the planned orientation of the well, along with the locations of nearby monitoring wells. We hung some HBT data. You can see the lithology there implied in the different colors. And again, this was really valuable in helping us optimize well design details and location and configuration. These path lines show the anticipated treatment zone, capture zone, and then these dots represent essentially timestamps, or you could think of them as particle paths. The cool colors represent short times and the red long times. And you can see within the treatment zone there on the right, those particles move through faster, just like on the first video I showed. One more comment. Before we proceeded with field installation, we considered how an HRX well approach might consider to other conventional flux control technologies. So if your objective was to create a clean line sort of in perpetuity, so control flux across a plane, the other two practical or conventional alternatives would be a pump and treat system, a series of wells along the transect, or a funnel and gate PRB type of approach. And we compared them, against some conventional criterion like, overall protection of human health, effectiveness and permanence, likelihood to create reductions in toxicity, mobility, and volume through treatment, implementability, sustainability, and life cycle cost. And they all compared very favorably. Of course, the HRX well has the potential to have a much higher sustainability benefit. There's very little ongoing energy and certainly no consumptive water associated with it. And the other thing I'd highlight is that the life cycle costs were right in line. In fact, our initial calculations came out a little bit lower than other conventional technologies. And so far, our field implementation, continues to validate sort of that cost range. A key assumption in this case would be that the HRX well itself has a treatment width of about 50 feet, and so to treat a target width of 150 feet, you'd need 3. Obviously, those costs will go up if you needed 4 or 5. The cost for this particular well is probably, additional wells would be $250,000 to $300,000 a well. So even if you went up to 4 or 5 wells, that doesn't, price the HRX well out of the range compared to the other technologies. So again, based on this, we proceeded with field installation last summer, late July, beginning of August. Upper left, you can see the completed hole, and then that's the 18-inch reamer going back through the hole. Bottom left is the placement of the screens and the kind of the welding of the casing. In the middle there, that's one of the PVP monitoring cartridges. So you can see in the driller's hand, the kind of the top we're about to bolt down, and in his hand, he's actually holding the PVP instrumentation. Top right was the well development activities and jetting. And then bottom right is sort of the final footprint on the inlet side, and it looks like that on the outlet side, and then that's really all the footprint you have. And conceivably, this could be placed even subgrade, but you need quite a large vault to do that. All right, so I'll talk about some performance data so far. So these are some example PVP data sets from the outlet side. So again, this is the small scale tracer test tool that's monitoring velocity in the HRX well itself. And these are these data, of course, are pretty clean, and if you can see the elapsed time is quite short, tenths of hours for that tracer to break through. And these translate to velocity within the media of about 8 to 10 feet per day. And our goal was between 5 and 10 feet per day. So we're right in line with what the model suggested we should be able to do. And just in context, the groundwater velocity in the aquifer is around 1/10 of a foot per day. So dramatic flow and velocity enhancement. Based on that velocity, we got a residence time in the ZVI of about 9 days, which we were targeting 8 to 20 days. So that's consistent with the design. And we're still working on finalizing the calculations of treatment width, and we're updating the numerical model based on some additional site data, but it's looking like our treatment widths are in the 40 to 60 foot range, which is consistent with model predictions. Also, we did do a short-term pumping test where we placed a pump in the inlet screen, and rather than bring that water to the surface, we pushed that water through a packer into the cased section, and then it was forced through the treatment media and then out the outlet well. And sort of validated that engineering kind of design was feasible. And again, that wasn't the primary design for this site because it's a low permeability site, but for high permeability settings where you can yield more water, that can be used to enhance treatment width. And we'll continue to monitor performance through the balance of this year and into next. All right, so I'll share some concentration data. We'll start with this graph. On the left is the upgradient well, immediately upgrading the screen with only a few within maybe 20 feet of the stream, MW35, and you can see on the bottom there we have baseline and the days since well installation, and you can see pretty high concentrations. And then 92 days after well installation, there's a notable increase in the cis ratio to cis to trichloroethane, and not as severe later on. And then of course on the HRX inlet, that inlet should look just like 35D, but there's no TCE and quite a bit of cis, and that's likely due to the fact that we used a biopolymer, basically a guar, as part of the drilling fluid, and a lot of that fermentable carbon was left in the aquifer and actually even remains to this day. And in fact, you can see we had 2 inlet well samples. That second inlet well sample, 184 days after installation, we took a TOC measurement, and it was still 339 milligrams per liter. So we're getting some definite treatment benefit from ERD type processes. But despite that, you can see on the outlet side, dramatic reduction in cis concentrations. So we go from 4 or 5 ppm to 100 ppb, and even on the outlet at the 184 day mark, there's still 20 ppm of TOC. So clearly there's some ERD performance, but absolutely what's going through the HRX well, 5 parts per million of DC is getting treated. So sort of the chemistry is validated. And that's maybe a 98% treatment. And then we do have some brand new data from the monitoring wells on the outlet side. In fact, you guys are the first group to see this data set. Just came in yesterday. There's some really good data here. So again, this is the outlet side, and you can see a handful of monitoring wells, 3MW13 and 3MW14 on the top of the image, and then on the bottom, 3MW47 and 48. And these are, within tens of feet of the outlet screen. And our prediction based on the model was that we'd see treatment in these wells, between 200 and maybe 500 days based on the flow rates. And here's some data. Hopefully this is coming through for you to be able to see. The gray represents TCE, and the blue is cis, and so you can see clear treatment at MW13 pretty quickly after installation, and a coincident increase in cis, which again, there would be the influence of the guar from the development and installation process. And of course, we anticipate that to continue to decrease over time. Dramatic reduction at 14. That well has historically been between 20 and 30 ppm, and it's running around 10 ppm now with a notable increase in cis. 48, we're starting to see the trend. And 47, it's a gradual trend, but there is a difference from 11,000 to 7,800 on the most recent data set. So this is really promising, and I would say consistent, if not a little earlier than we expected. But also validating a treatment zone that is tens of feet and would be consistent with ultimately a 50 to 60 foot treatment width. All right, and with that, Michelle, I'm going to turn it over to you for the design tool.
All right, I know we only have a couple minutes left, so I'll try to work quickly here. We're working to develop a simple Excel-based design tool to simulate treatment and capture and treatment through the HRX well, as well as treatment costs and the sustainability parameters. When the user enters site-specific factors that affect design, such as aquifer properties, contaminant properties, media properties, installation and operating costs, this tool will ultimately tell us how much water we're capturing, the extent of contaminant treatment, and what that cost looks like. It'll be a conceptual design tool that will enable users to compare that out to other possible approaches that that may be considered for a site. So our goal is to use simplified equations, those based on Darcy's law that Craig showed earlier. That will enable us to have a very fast and user-friendly Excel-based tool rather than relying on more complex numerical models. However, to assure that the simplified equations are robust and accurate enough to guide design, we did work on building a finite element numerical model. And we varied a wide array of input conditions, and we compared the resulting output for the numerical model, for the simplified equations, and our actual field measured data. As you can see in the table in the top left, the numerical model and the field data match really quite well. The simplified equations aren't too far off, but what we're working on now are adjusting those simplified equations to account for some of the microscale effects that aren't currently accounted for in the simplified equations, but are important once we start operating at scale. And so ultimately, we anticipate something that'll be fast, easy to use, and give a lot of information with reasonable amount of input that would be at a user's fingertips. We're also going to be doing site sustainability analysis using SiteWise, a common tool to determine some of the key sustainability metrics such as energy use, greenhouse gas emissions, and safety across the life cycle of HRX well installation and operation. And these will be used for our ESTCP project. We'll be calculating the same parameters for an equivalent pump and treat and PRB treatment system, similar to the early comparisons that Craig showed you. And so we'll be doing this in a great deal of detail for the project, but ultimately we're going to be rolling up these sustainability metrics into the user-friendly design tool. So the tool will incorporate many of these sustainability parameters. The preliminary analyses, as Craig mentioned, showed that the impact of the HRX well treatment looks to be lower than comparative technologies due to passive flow, less water use, and also really effective and efficient use of the media. So this has been a build-up process, and we hope to have something ready to roll to evaluate in more detail in the next couple of months.
Great, thanks, Michelle.
Yep.
So maybe just in closing, I put together just a few key points. Just if there's anything you got to remember, I would say the HRX well, the concept is ideally suited for sites where you're looking for in situ mass flux control. It's at least as we've shown here, a passive operation, and for the right geologic conditions per well, treatment widths of 50 feet or more are possible. As I mentioned, capture zone size could be enhanced with pumping. There are a wide variety of reactive media options, and therefore applicable to many contaminants, including potentially PFAS. There's very efficient media usage. And actually the change out of those cartridges is straightforward. We recently did a servicing and had no trouble at all pulling a cartridge out. One of the monitoring cartridges and placing it back in. Limited above ground footprint, no ongoing energy, water, O&M requirements. And again, just to restate, there's a real favorable life cycle cost and sustainability comparison, at least for many applications to pump and treat PRB. And the picture got offset there. So I'd like to just acknowledge there's a broad team of folks working on this. So I won't call them all out by name, but they all provided critical support. And if you're interested, we do have a couple of publications that came out in this past year, one in GWMR and one on remediation, one in remediation that provides a little bit more detail on the concept. And with that, we'd be happy to take any questions, I guess.
Alrighty, thank you, Craig and Michelle, and thanks for everyone who attended and stuck around for the end. We'll do questions now, so if you want to use the GoToWebinar question pane on the right hand of your screen, you can enter your questions. While we're waiting for those to roll in, I just want to do a quick reminder that this webinar was recorded. So if you're interested in the recording or the PDF of the slides, please contact me and I can provide you with those and also with a link to the recording once we get that posted up. So we have a couple questions here. Start at the top here. In the case study, how can you tell that the concentration reductions observed at the wells near the outlet are from treatment rather than just dilution from the treated well, or from the treated water exiting the well? You need me to reread that, or?
I think I understand it. So that just to be clear, the process by which those down gradient wells would be treated is through flushing. That is, cleaner water is coming out of the well, and then the front of cleaner water is intercepting those down gradient wells. So there's no treatment process in the aquifer. All treatment occurs in the HRX well. And then in a sense, you can think of the HRX well injecting clean water at the outlet stream.
All righty. And then also, Craig, do you see applications where single-ended wells could be used?
Yeah, for sure. There's no reason why hydraulically a single-ended well wouldn't work. A double-ended well makes it a little easier when you're trying to both build and develop the well and then put the cartridges in and out. And in this field application, we had plenty of access on both sides, so we decided to have a double-ended well. But I think there may be some logistical challenges that are a little bit trickier with a single-ended well, but certainly there's no reason hydraulically why you couldn't have a single-ended well.
All right, and then do you have a way to control the residence time for treated media? Is there limitations to the benefits of the system?
Yeah, so I think that is also one advantage compared to a conventional trench-based PRB. I mean, with a trench-based PRB, your residence time, you really have little control on. You know, you can make that trench only so wide as the bucket, or maybe a little bit wider, and then that's it. And if that's not enough contact time, you might need a second trench down, a little bit further down gradient. With an HRX well, you can adjust residence time two ways. One is by lengthening the HRX well, so just make the run longer. And in this case, we only used 7 cartridges, but we had space for 4 or 5 more, so we could have put more cartridges in. So you can lengthen the well. You can also slow down the water in the well if you want by using media that is not quite as permeable. So you can use less permeable media. Now that will reduce your capture zone. The permeability enhancement goes down, so your capture zone width goes down. So there's a little bit of give and take, but you do have, I would say, some more engineering knobs that you can turn to optimize for residence time.
All right, and then we have one last one here. What percentage of the costs are associated with the horizontal drilling versus the well casing and reactive materials?
Yeah, good question. I don't have that off the top of my head, but I'm going to say probably no. Nobody quote me on this. I'm just going from memory, but I think the drilling costs all in, including the cartridges and the media, were probably $350,000, and probably the median cartridges were 75 of that. So it's sort of that ratio. The drilling costs, were higher in this application because we had some specific challenges at Vandenberg that aren't, always present, not related to the technical issues, but just sort of Elon Musk was launching things and that shut us down a few times, and some other issues. So I don't know, hopefully that was helpful. It's a portion of it, but a small portion. The bulk of the installation costs are around the drilling.
Alrighty. If your question was not answered, we do have all the questions in a report that we will have Craig or Michelle reach out to you directly for those. And if you guys think of any questions after this webinar, feel free to contact any of us and we can answer those questions for you. So I'd like to thank Craig and Michelle one last time and everyone for coming, and have a great day.
Thank you so much.
Thanks, everybody.